Are we being boycotted? Okay. Unusually small class. No, actually, this is the last meaty lecture, but there is some stuff that I definitely want you to see, and that I hope you will pick up on. So it's actually an area of geophysical research that I've been involved with for quite a while, and it's something that has got a lot of importance in the mining industry, especially. It's becoming more important in water resources and in sort of environmental contaminant studies, perhaps finding hydrocarbons. And it's just one of these things that at one point people didn't even recognize that there was a signal there. And then gradually as instrumentation got better and people looked a bit more, and they can see, oh, wait a minute, there's something kind of happening here. Maybe we should take a look at it, try to understand what's going on, and then eventually it gets to the point where this is actually mainstream and it has a very big piece of information. The basic idea, and we'll go through it in more detail, is that the Earth can actually act a bit like a capacitor. If you try to drive a current through some rocks, then they build up charge and they act like a capacitor. And when you take that driving current off, then the capacitor will discharge. And if you ever have any kind of motion of charge, then you can measure either an electric field or a magnetic field. So the process is called induced polarization. So I'm going to talk about the basic principles, acquisition, pseudosections. There'll be part of this in here is almost identical to what we did last time in DC resistivity, so it's going to be almost a bit of a review, and then show you history. So the idea is as follows. Here's what we did last time with DC resistivity. We had a source. Remember, we just had a generator here, and then we could measure the electric potential any place else. So if we had just a current source that went up like this, so this is 0, this is positive, it's on, turn it off, dot, dot, dot. If we measure this potential, it's actually got the same kind of shape. When the current goes on, the voltage rises. When the current goes off, the voltage drops down. And so that was the information. We used this voltage here as well as the geometry of the system to estimate what the apparent resistivity was for each measurement. In the early 50s, they were doing this, especially for mineral exploration, and they found the most bizarre thing. So they turned the current on, as they would ordinarily, and then when they looked at the voltage immediately went up, but then instead of just plateauing at this value, it just kept rising, rising, until it sort of asymptoted. And then when they turned this off, it dropped down to a certain value and then decayed. So it was very surprising. They initially had no idea what it was. But they did refer to it as something. They called it over voltage. And the reason it's called over voltage is that you get you end up with a higher voltage here than you would when the ground was like this. So the question is, what is actually causing this? And the answer is that it's really kind of complicated. And at the real microscopic level, it's a bit hard to figure out. If you look at rocks they can have a fibrous network like this. You get disseminated sulfides and things like that. And that surface area and volume is really complicated. This is filled with electrolytes, fluids that have ions on them. And all of these things in here might have charges on them if they're little sort of clay stringers or something like that. The phenomena that we're going to talk about for induced polarization actually has its roots in this kind of microscopic origin. The value of this chargeability, as we're going to call it, which is the character or the ability of materials to actually act like capacitors, changes. We've got things like pyrite, which have very large values, chalcocite, copper graphite, and back down to hematite. So again, sort of order of magnitude or 2 orders of magnitude different. And these are all minerals sort of at a 1% concentration. If we look at different kinds of rocks, groundwater has no chargeability. Alluvium, gravels have smaller values. Gneisses might be bigger. You get up to shales or sandstones, they have bigger numbers. And when you get up to sulfides, you can get actually very large numbers. These numbers are all in what are called milliseconds. I'll explain how that goes, but at least that gives you sort of a relative value. So even though the fundamental physics might be complicated, there is a very, very simple kind of physical model that if you keep in your mind helps you sort out exactly what's going on. And the idea is as follows. Suppose that we've got a system in here. So here's a rock. So this might be, this is now in the order of, microns in here. And this is a pore throat. So we've got positive and negative ions in here. And everything at some stage initially is just in complete equilibrium. Now, suppose I take this system and I put onto it an electric field. So I'm going to drive an electric field this way. You could think about that as having a positive end of the battery here and a negative end of the battery here. So I've got an electric field that goes this way. So what's going to happen? These positive charge, so the electric field can be thought of as being a big positive charge over here and a big negative charge over here. If we think about what's going to happen here, positive charges are going to repel, right? So the positive charges are going to try to go this way, but they might get caught up in a pore throat. So as I put on this electric field, I might expect this equilibrium fluid to change a little bit with the negative particles going this way, positive particles going this way. And the same is traveling here. The positive particles are going to want to travel this way, and the negative ones are going to travel this way. And if you've got a pore throat that's fairly small, then it's not possible for these guys to get through. So in the end, there's going to be an equilibrium state here in which we've got a net positive charge over here and a net negative charge. And then if I kind of stand back and I look at this whole system, it's just like, okay, I've got a great big positive charge over here, I've got a negative charge over here, I got dipole. I've got sort of an electric dipole that's sitting here. So if I have an electric dipole, that's going to give me, a potential. So if I'm sitting someplace up here, I see this positive charge, I see a negative charge, there's going to be an electric potential. So with all of that, you can start to see how you would kind of put this together. You start off with neutrality, and then that you switch. So here's the current, and now here's going to be the voltage. the voltage, as soon as I turn that current on, immediately rises. That's just our DC resistivity effect. But then as time goes on, I'm going to get this accumulation of positive charges and negative charges. So that's actually going to cause my voltage to increase. And then it's going to asymptote at some point when I've got the situation completely saturated. I'm not going to be able to accumulate positive charges here ad infinitum, because if I get too much positive charge here, the next one that tries to come into here is going to get repelled. So you can see that, okay, there's going to be some kind of steady state, some kind of equilibrium. So this is going to go on. It's going to reach some type of equilibrium. The moment I turn this off, I lose my DC potential, but these charges are still there. This is a viscous fluid. It's going to take some time for these charges to equilibrate back to their initial position, and eventually they're going to go back to neutral. But as they're doing that, this voltage that had been built up gradually decays. So that's the essence of what's going on, and this is a really good way of kind of mentally thinking about it. And you can understand what happens the moment that I put this current on, or electric field on. I'm going to start to build up charges. They're going to build up, build up, build up, reach a steady state value, and then when I turn things off, those charges are going to decay. This portion here is all just due to this accumulation of charge. And because we end up kind of getting a dipole, we tend to refer to this whole process as induced polarization. So I'm getting kind of a polar distribution. It's being induced by the outside, so it's induced polarization, or IP. So that's where that comes from. Good. Yeah. So how do we record values, or what do we do for data? The data can take many forms. The first thing to think about is that anything that's somehow connected with this voltage decay, which we're going to call B sub S, which stands for secondary voltage. So anything that's connected with that is somehow related to the IP effect. And we have many different ways of describing it. This quantity that we've got in this particular diagram here is labeled as V sub M. This quantity that we have here is V sub T, or V sub S, as a function of the time. And this ratio of this quantity here, Vs, at some time t is equal to 0, over Vm, is equal to what we're going to call the chargeability eta. So our chargeability is kind of this ratio of what the final value of the voltage is compared to what's left when you immediately turn that voltage off. So one, the definition of sort of intrinsic chargeability is given by this quantity here, Vs over Vm. And that's going to take on values between 0 and 1, right? Because this guy has to be something below here. And so the maximum it could be is about 1, and the minimum it could be is close to 0. So eta, the chargeability, is in this range here. Sometimes that's called intrinsic chargeability, and because This is just a ratio. This has no units. This is dimensionless. So the intrinsic chargeability has no units and it's bounded between 0 and 1. Okay? We could measure, as far as our geophysical data, any characteristic of this curve. It actually turns out that this is a really difficult thing to measure, and you can appreciate that because you're measuring, you can measure this value, okay, but then it takes time to turn things off, and turns out there's also kind of other complications that happen. So it's actually not possible to measure this secondary potential right at this time here. Earliest, there's some early time channel that we can measure it, or we can measure it at somewhat later. Some of the systems, in fact, most of the systems now, will have a number of channels of time. So this is time going on here. They'll start after a slight delay, and they'll start measuring what this potential is as a function of t. And then your IP datum could be the ratio of any of these values at any particular time t to whatever Vn was. So again, that would be a dimensionless quantity because it's volts over volts. It's usually a pretty small number. So then we multiply it by 1,000 and say, well, that's sort of millivolts per volt. Another thing that you could measure is maybe the integral of this curve out here over a certain length of time. And there was an era in geophysics that it was kind of standardized, that there'd be a start time t1, stop time t2, and the instruments would measure the integral of this curve here as being a representative of the chargeability. So in that case, the value of the datum was the integral from T1 to T2 of the secondary voltage, but again, normalized by whatever that primary voltage was. So the units here are Vs, volts over volts, so that cancels out, but then you're integrating in time, and so that gives you a unit in time, and usually we convert that to milliseconds. So if you go back to those first charts, that's what the units were. They were in milliseconds. Okay, so just to recap, turn the current on, we get something that looks like this. We got an over voltage. Turn it off. There's some ratio here between what this secondary voltage is to the primary. That could give us our intrinsic chargeability, bound between 0 and 1. We could measure the value at a point in here and take its ratio with this value. So that's a number, volts per volt. That's a datum. Or we could measure some random area. The point is, all of these things give us some intuition that, wait a minute, there's some kind of a decay here, and so something's happening. So that's sort of the rationale for all that. You could also have, and you will see this, and that's what kind of flip this out, you could also do the same kind of thing in the frequency domain, where instead of having a time plot like that, your voltage or your current source, is just a harmonic. So it's the same kind of source that we had in that loop for the EM31. So this is I of t. And now again, as in the EM31, you're going to receive a voltage. It's also going to be sinusoidal. It's going to have that same frequency, but it's going to be shifted a bit. So it's maybe shown a little bit better here. So here's our current I of t. Here's the received voltage. Looks like this. It's got whatever amplitude it has. And we notice that it's got a phase shift here between this and this. So that's also indicating, wait a minute, there's some kind of a delay that's going on. And that delay is representative of how much time it's taking for those charges to build up. So that would be a datum. And the final datum that we have is something called a percent frequency effect. And what that does is it works with a current that has got kind of a fast switching. So if I take a current source and I make it positive and then negative, positive, negative, but I do it at a very small time scale, then what's going to happen here is the moment I turn this on, that overvoltage is going to start to build up. So it's going to come up this way. But it never gets a chance to come up to its final value because now I'm switching it off in the other direction. So it gets switched off and then it comes down like this and then kind of repeats like that. So the point is I get to have a certain upper value here that's obtained before I switch things off. So if I change things around and I say, oh, I'm going to have a current that is, is on for a much longer length of time, then that overvoltage has more time to build up. So the current charges build up, and I actually receive this point here. And then I go back down like that. So you can see that this number up here is actually larger than this one. So again, that's telling you something like, wait a minute, there's charges that are being built up here as a function of time. And so I could use that number just to be diagnostic of something being chargeable. So if we take these numbers here, we've got an apparent resistivity from here, we've got an apparent resistivity from here. I can subtract them and normalize by 1, multiply by 100, and I get what's called the percent frequency effect. And so that's another IP data. So you can see there's a whole bunch of ways of actually getting something out that's representative of the idea that, wait a minute, there's charges being built up here. So I've got ground that's chargeable. So we could do it in the frequency domain. We could do it in the time domain. And we've got different numbers. Doesn't matter. They're all telling us that there's something interesting happening there. Okay, so how do we collect the data? Well, as you might have expected, the data are collected just as we would do it with a DC resistivity experiment, right? Because this is what we did for DC resistivity. We had a current that was going on. We've got something that looks like this with a current, and then we've got some potential electrodes, and turn the current on, measure things, and then get this apparent resistivity. And then we plot that up in terms of pseudosection. So this is exactly what we had before. So remember how we did that? If you've got, this was a dipole, that's when we've got a dipole current source and a dipole potential field. And then we wanted to plot that on a plane. So we just did these 45-degree angles. And then we looked at where they're intersecting, and they said, okay, I'm going to plot the datum there. For the DC resistivity, we plotted the apparent resistivity. So we took that voltage divided by this and plot the apparent resistivity. For chargeability, we're just going to take whatever number we get there and plot the chargeability at that point. So it's going to look perhaps somewhat similar, but the units are going to be quite different, and the interpretation of what is going on will be different. And then again, for building up the pseudosection, remember we did it's kind of a sounding and profiling mode where we just kind of continue moving the whole system along, separating transmitters and receivers, taking the apparent resistivities and plotting them up. So now we do exactly the same thing, except we're just going to plot out the chargeabilities. Okay. So again, we will have something that's pretty similar to what we saw before, but now I've got a chargeable block. So the conductivity of this block and the conductivity of that background are the same. But this block here has got I don't know, maybe disseminated sulfide in it, or maybe a bit of graphite or something, and it's actually chargeable. So if I go ahead and I do that same dipole-dipole survey over top of here, plot my pseudosection, then I'm going to get out, a picture that looks like that. And as we add the DC, you can see that, okay, that's got some information, perhaps about this. It's not looking exactly the same, but there's a peak of chargeability happening right here, and maybe if I drill down here, I might hit something. This axis here is not true depth. It's a kind of like a pseudo depth. It's really just recording the end spacing, the difference. I don't think I mentioned that. So in a dipole-dipole survey, here's my current electrode. So these guys are all the same distance. So this is A. That's A. You're doing at the same distance. And then if I have my voltage here, then the separation of this dipole from here is 1 times A. If the one's over here, and it's 1, 2, 3. So anything that's plotted here would go at that level survey of n equal to 1. So it's 1 unit distance. This guy down here, over here, would be n equal to 3. So that's what these numbers are. So it's the n spacing, 1, 2, 3, 4, 6. Right? So as you go down, as you increase n spacing, you're somehow looking deeper, and that's all that picture will convey. Again, if we add little bits of stuff, now these things are all the same conductivity, no change in conductivity, but they are different chargeabilities. And again, clays, graphites, sulfides, those are the big ones that perhaps from your perspective, clays are important. So if you had something that looked like that, then now your pseudosection just gets all bundled up, and you just can't see anything. And one final one, and it's got another complication, because if you have topography on any of these surveys, then it turns out the topography makes a big difference in the signal. And if you had a chargeable body here and another chargeable body here with a slight surface chargeability, your pseudosection looks like this. So this pseudosection is a picture of the data. It has absolutely nothing to do geologically with what's going on here. Right? There's no one-to-one correspondence. So now we're back to the same situation that we were before in the DC resistivity, and that is that basically we don't have any choice except to kind of invert the data. I didn't really get a chance to go through this the last time, and I don't have another chance this time. I just put this up just to kind of give you a feeling that when you invert data, there's actually quite a few steps that you need to go through. But the basic essence is, in fact, for the 2D, so we've got this kind of pseudo section. So here is our data, and then when we go to do the inversion, we take this Earth model, which has got X along here, Z along here. We divide it up into a whole bunch of cells, each one which has got a particular chargeability. So this is the first cell that's got chargeability 8 of 1, 8 of 2, 8 of 3, and here we go down to 8 of 400,000 or whatever. Right? So we got all of these cells in here, and our goal is to adjust the values of these so that we reproduce the data. So it's nothing different than what you ordinarily do, but the size of the problem gets much larger. And you need to also to worry about non-uniqueness of the problem, and therefore we generally need to put some kind of a priori information on about, you know, we want to have something that's geologically sensible and sort of smooth and make some sense. So that's a whole story in itself, but that's basically what you end up doing. And to the relationship between this chargeability, so this is going to be like a vector, right? So our chargeability as a vector is like, okay, eta 1, eta 2, eta 3, to eta 400,000, whatever. So that's just like this big vector of numbers. And then we get some data that we've measured up here, all the values of the pseudo section, different n spacings, different location on here, so that the data, you know, might be D1 to Dn, you know, so maybe n is, you know, 1,000 data or something like that. The relationship between these is a linear relationship. J eta is equal to D. So D is our data, N is our big chargeability model, and J is a matrix. So if I was a bit more explicit and I said, oh, that's got capital M elements, so then eta vector has got, you know, size M, D has got a size N. So J, the matrix J, has got to be, you know, an N by M matrix, right? So that we've got J is N by M, eta is an M length vector, and D is an M length vector. So this gives us our system to be solved, and we go ahead and we do that. So in our case, these data could be anything that we had before. So they could be, you know, millivolts per volt, they could be milliseconds, they could be PFEs, they could be milliradians, that doesn't matter. We take whatever those data are, and we compute. What we need to do is to compute this sensitivity function. The steps involved are the following. We're going to go out and we're going to do a DCIP experiment. Okay. So we're going to collect. Here's our current, and here's our potentials. And we're going to collect these data as well as some IP data. And we're going to try to invert those things. So the very first thing is what we did yesterday, is we took these potentials, converted them to pair resistivities, and then we tried to find a resistivity or conductivity structure that gave rise to those data. So that's the DC experiment. So this, we now have a map of electrical conductivity or electrical resistivity. Good. The next step for working with the IP is that we actually need to use this guy, this conductivity structure, and we're going to use that to compute this sensitivity quantity here, J. So that my mapping, if you like, between the data and the chargeabilities is a sensitivity function, and I actually need to have the conductivity to do that. And then once I've got that, then I'm back to solving that problem, and now I can solve for the chargeability. So it's always a two-step process. And if you're connected with anybody who's doing the DCIP experiment, they're always going to do it in two steps. They're going to take the voltages, compute the conductivity, and they're going to take that conductivity compute the sensitivity, and then solve that chargeability data. So always the same thing. So just to show you how that can work in this particular case. So let's take that chargeability model. Here's our pseudosection. If we take this and invert the chargeability, that's what we get. So this is great, right? We've got a nice localized body where the prism is. It's not nearly as sharp, but within the context of our inversion, we're actually asking for something that was a bit smooth. So this is pretty nice. It's at about the right location, both in depth and certainly horizontally. And if we take this and we forward model it, that's our data. That's our predicted data. And so this predicted data is a pretty good match to the observed data. So mission accomplished, right? We've taken our data, inverted it, found something, finds that it reproduces the initial data satisfactorily. Come down to this guy, it's got more stuff there, right? Now the pseudosection is completely uninterpretable. You can't see anything there. But if you go ahead and invert them, you can start to see, first of all, I've got my prism, but even more than that, I've got these little guys that are sitting up here. So my pieces of graphite or whatever. My predicted data look like that, which is like that. So this is great. Right? So we've got a data map that makes no sense at all. Unlike, so this is actually very much unlike, the magnetics, for instance, right? You have a magnetic map, you look at the map, I mean, you can see structure, and you got an idea of what's going on here. This kind of stuff, you look at it, and very often you can't tell anything. So it's only after you unravel it with inversion that you've got some kind of good agree between the observed and predicted data. And this one I think is especially interesting because we've got this chargeable body here and another chargeable body here. And if you generate the pseudo section of that, it actually looks like, oh, I've got a great big chargeable body here. Well, if you wind the clock back a couple of decades ago, people would have looked at this and said, terrific, look at that. There's a great big chargeable body. It's probably a sulfide down there. Let's spot a drill. So they probably drill right down like that. And that would have drilled right down through here. So they missed, easily to miss everything just by kind of making some quick opinion from that. But if you take that, go ahead and invert it. And this is what you see. So you got chargeable block here and a chargeable one. You don't see all of this stuff that's really going down here. And that's simply because the experiment was such that we weren't really driving currents down here. So we didn't really ignite this part of the object completely. So there's not very much information coming from here. So you do the inversion, doesn't have to put anything there, and you end up with something like this. And similarly here, you're kind of smeared out. But from the point of view of geologic interpretation, you now have something, you've got a body here, you've got a body here. If you drilled in here, you'd have been very happy. So I now want to go back to this example that I had talked about last day, because we did the DC resistivity, and we ended up with a great geologic model, but one that really wasn't of particularly interesting from mineralization viewpoint. So just to refresh your memory, this is what we had. So this was in Northern Australia. So this was like 3.5 kilometers by a couple of kilometers. There's 10 lines of data, and the data were either pole-dipole or dipole-pole. So in this case, a dipole-pole, so the potential dipole is like this, and the current pole is out here. And remember, the other needs to be another current, so it's way in echagon. And we saw this red here, which indicated material that was really pretty conductive. In fact, this stuff really is very conductive. If we flip things around, so now we're energizing things differently. So you can see how important this might be. So let's suppose I've got something, that's sitting out here, and now if I put my current electrode in here, and then I'm measuring the potentials, so my currents, are kind of going to get sucked through here. It's a very big conductor, so I'm going to get some kind of distribution of charges on this guy, and that's going to give me some measured potentials. But if I go the other way around, if I put the current on this side of the body, now I'm sort of igniting this body in a very different manner. So that all my charges are going to be different. So I'm going to expect my potentials to be different. And that's what we see here. When we look at this pole dipole, there is still some manifestation of sort of higher conductivity, but it's really very different than this. So just igniting the Earth from different angles gives rise to different data sets. But the thing with all of these pseudo-sections is that there's only one Earth model there, right? So all of these things are somehow kind of encoded information about parts of that model. What we really want to do is sort of combine them all together. And so we did that through the inversion. That helps. I won't do the movie again. We'll do another movie at the IP. But remember, here was our block of conductivities. We sliced this in a couple of different directions, and then we did this isosurface thing where we progressively made every pixel that was less than a certain value, made that completely transparent. So in the end, the only thing that we end up with is this conductor here, and that was that black shale unit, which geologically is interesting. From the point of view of mineral exploration, it was no interest. If we kind of took a snapshot through at some level, some plane in that, you can see how this big, really conductor comes through. So that's, conductivity was interesting, but not what we wanted. So let's go to chargeability. Same scenario. Here's our pseudo-sections. Now, if you remember in the DC resistivity, pseudo-sections came all the way down to a point. They're doing that because the transmitter and receiver are way long ways away. However, these are secondary fields. Remember those voltages, like a typical voltage, kind of comes like this. So the numbers that we're seeing out here for chargeability, like they're really small compared to these guys here. So because the numbers are small, when you get to really large offsets between the transmitter and receiver, the signals are so small, it's basically noise. So these have to get cut off. Other than that, it's the same pseudo-section. So again, this was a dipole pole. Oops. Guess I don't have the other one. And then we did the reverse, the pole dipole. So now we take it's the same block, and we can do the same slicing. But now notice how much difference, right? Look at this big red stuff that's sitting up over here. So we still red over here, but we've got now another red piece that's coming through. Right there. See this guy that's coming in here. And now we're doing the isosurface. And again, so we're just turning it around, and now the charge, any chargeability is less than a certain value becomes transparent. And there's the final value. So this is now chargeability. We still notice there's something chargeable up over here that is actually connected with this black shale. So there's, it's chargeable, but it turns out not to be economic. This stuff in here, however, is a chargeable body that is mineralized. So what we see is that we've got a nice elongation of this. If we take a look at the electrical conductivity, we'll find that there was some manifestation in here about kind of a mid-range, intermediate sort of conductivity, which is what they felt the mineralization should be. So mineralization should be kind of moderate conductivity, not nearly as much as this, a little bit bigger than the background, and really quite chargeable compared to the background and that part. So there's the results. So here's what kind of comes out from the conductivity. Here's what comes out from the chargeability. So it's kind of like you've got two different physical properties, conductivity, chargeability, and different rock units and different mineralizations manifest different relative amounts of these. And these two pictures are instantly interpretable from a geologic standpoint. Anybody looking at that can figure out exactly what's going on. So that's it. 3 seconds left. Time for a quick question. Hasn't been all that much time for interaction questions, but yeah.
How can you tell by looking at a pseudo section what type of array survey it is? Like if it's dipole, or
oh, I don't know how you tell.
Okay.
Yeah. They should provide that information, what the data acquisition is, to get those appearances. Okay, so that is basically the end of the material for the course. As we go through, so Friday we'll have a team-based learning. So it's going to be based on this material, so the DC resistivity, the IP for waste dumps. That's becoming more and more common these days. There's all kinds of places that people have, dumped garbage. They are now degrading, and stuff is getting out, leaching into local groundwater supplies. It's become a big problem, and it's going to get bigger. And IP is probably one of the most effective ways of kind of understanding something about that waste stuff. So I think you'll be really interested in this, and it well kind of ties what we just talked about together. Then Monday we'll do a quiz, and then that kind of finishes up all of that technical material. And I got Wednesday and Friday to kind of do some recapping and ask some questions. And, yeah, party. There you go.